Hello everyone, welcome to this video. In this video, let us understand the problems in Module 1 Electronic Circuits. So the theory concepts we have discussed already. Now let us see the problems one by one. The first problem, a mains transformer having turns ratio 44:1 is connected to a 220 volts RMS mains. If the secondary output is applied to the half wave rectifier, determine the peak voltage that will appear across the load. This problem is on half wave rectifier. First let us write the half wave rectifier circuit. Here the transformer ratio that they have given. So the transformer ratio will be 44:1. Means this is the primary coil, this is the secondary coil. Primary coil will be having 44 number turns and secondary coil will be having 1 turn. And here is the diode and a load is connected like this. This is RL. So in the problem itself they have given 44:1. It means the number of turns in primary is to number of turns in secondary coil, and it is connected to a 220 volts RMS value or RMS supply. So this is 220 volts input, which is given in root mean square value. Always we are going to take the input values with respect to RMS value. That's why they have already given it. And the secondary output is applied to the half wave rectifier. So I have connected a diode D1 here. Determine the peak voltage that will appear across a load. The voltage we need to find out. We are going to get the voltage V out across RL. The peak value of this V0 they are asking. So for this, first we need to get to know what actually the voltage available across the secondary coil. The primary voltage is 220 RMS. The secondary voltage we need to find out. We know that this is a step down transformer. Why? Because the number of turns in the primary coil is more than the secondary coil. That's why it is a step down transformer. And the equation for calculating V2 is N1 by N2 is equal to V1 by V2. By using this formula we can calculate V2. What is N1 here? It is 44. What is N2? It is 1. Is equal to V1 is 220 and V2 we don't know. We need to calculate V2. So here if you calculate V2, it is 220 divided by 44 and the value is 5 volts. This is also a RMS value. We need to write it as 5 volts RMS value. And once we obtain V2, this V2 is available now, we need to calculate the peak voltage. So peak voltage of this V2 is VPK. Peak voltage will be equal to, this peak voltage can be calculated as root 2 times V2. Means observe here, this 220 volts is an AC signal. The same AC signal we are getting at V2, that is also AC. But because of the step down transformer, it is reducing 220 volts AC to 5 volts AC. So this is an AC signal. So we need to calculate what is the peak voltage. The peak voltage is not same as 5 volts, right? The peak voltage is root 2 times V2. So root 2 is 1.414 into 5 volts. So we got 7.07 volts as the voltage available at the secondary coil and the peak value of that is 7.07. Now we need to obtain the voltage V0. What is V0 here? V0 is the voltage drop across the diode. We need to find out. We got to know that 7.07 volt is the voltage we are going to get at the secondary coil as a peak voltage. We need to find out the peak voltage of V0, which is across RL, but there is an voltage drop here across the diode. So we need to subtract that voltage drop from this minus. What is the voltage drop across this diode? If this diode is silicon type, the voltage drop is 0.6. Because of the 0.6 volt is the cut-in voltage of this diode. This 0.6 volt is required to turn on this diode. That's why we say this is the voltage drop. So we need to subtract 0.06 from this. So V0 is 6.47 volts. This is V0, the peak voltage appear across the load. The second problem is on RC smoothing filter, where the input is taken as 240 volts with 50 hertz, you can observe, operated with a half wave rectifier. It is connected here and consisting of R1 is equal to 100 ohm, C2 is equal to 1000 microfarad. Micro in the sense it is 10 raised to minus 6. If 1 volt of ripple appears at the input side of the circuit, determine the amount of ripple appearing at the output. You need to find out what is the amount of ripple present in the output. So V ripple expression you guys know. What is V ripple? Is equal to XC divided by root of R square plus XC square. What is R here? R, they have given the value of the resistance. It is 100 ohm they have given. What is XC? XC is reactance of the capacitor. So the reactance they have not given. They have given only the capacitance value. So what is XC? The expression for XC is, we need to calculate XC here. It is 1 divided by 2 pi FC. What is F here? This is the frequency they have given in hertz, and then capacitance value also they have given. It is 1000 microfarad, and pi we know it is 3.14. We can calculate XC. So substitute these values. 2 into 3.14 into 50 into 1000 into 10 raised to minus 6. This gives XC. It is 3.18 ohm, the reactance of the capacitor. Now after obtaining XC, we just substitute in V ripple expression. So V ripple becomes, V ripple is equal to 3.18 divided by under the root 100 square, R square, R is 100, and plus XC is 3.18 square. So if we calculate this, it becomes 0.032 millivolts. Okay, sorry, this is 0.032 volts. We can write it as 32 millivolts. Okay, 32 millivolts. The next problem is on Zener diode as a voltage regulator. The question is, a 5 volt Zener diode has a maximum rated power dissipation of 500 milliwatts. This is PZ. What is this 5 volts? This is VZ. Zener diode is designed in such a way that it should regulate the voltage to 5 volts. That is the meaning. And maximum power dissipation they have given, that is PZ. If the diode is to be used in a smaller regulator circuit to supply regulated voltage of 5 volts. If the Zener diode is designed for 5 volts, obviously the regulated voltage will be 5 volts only. To a load having a resistance of 400 ohm. What is 400 ohm here? This is RL. Determine the suitable value of series resistor for operation in conjunction with the power supply of 9 volts. If we give power supply of 9 volts and we are obtaining 5 volts as output and RL is 400 ohm and the diode voltage VZ is also 5 volts, we need to calculate the suitable value for RS. Okay, here it is asking to calculate the suitable value, means we know the expression for RS maximum and RS minimum. Let us calculate those two. RS maximum is, we know that expression RL into Vin divided by Vz minus 1. This is the expression for RS maximum. If we substitute the values, 400 into 9 divided by 5 minus 1, it is 320 ohms. This is the value of maximum RS we can have. And also we can calculate the minimum value of RS what we can have. That is Vin into Vz minus Vz square divided by Pz maximum. It is in terms of power. So what is Vin? It is 9 into Vz is 5 minus Vz square is 5 square divided by Pz maximum. They have given it as 500 milli. Milli means it is 500 into 10 raised to minus 3. So if we calculate this, it gives 40 ohms. So this is RS maximum and RS minimum is 40. Now we need to select the suitable value. So for suitable value, we need to choose a value in between these two. So I am choosing round off to 150 ohm is the suitable value in between 320 and 40, so that it will be regulating to 5 volts. Then next problem, here the following data were obtained during a test carried out on DC power supply with load test and regulation test. It means this problem is on voltage regulator, okay, and related to DC power supply. Here the two tests they have given: output voltage when there is no load is connected, it is 12 volts. Output voltage with 2 ampere of load current is flowing through, means with load, this is 11.5 volts. At the regulation test, they are connecting the mains to 220 volts and we are getting 12 volts as the output voltage. When they are connecting 200 volts as input, we are getting 11.9 volts. Now we need to determine the equivalent output resistance. Output resistance means resistance output, R out, we need to find out, of the power supply, and the regulation of the power supply we need to find out. So what is R out? We know that output voltage divided by output current, R out means it is output. V out divided by I out is R out. Here we need to take the change in output voltage to the change in output current. Okay, since this is a power supply where the tests are done and there is a variation in the voltage and current, right? That's why we need to take it as change in output voltage to change in output current. It is 12 volts at starting when there is no load. When the current of 2 amperes comes into picture, it is changed to 11.5. That's why it is 12 volts minus 11.5 volts divided by the current change from 2 to 0, right? So it is 0.25 ohms. And we need to calculate the percentage of regulation or the regulation of the power supply they have asked. You know the expression for regulation also. Regulation is expressed as change in output voltage to change in input voltage. This is voltage to voltage. Into 100 if you do, this is the percentage. Okay. Here the output voltage is 12 volts, and then when the output voltage is changed because of the input change, it is 11.9. We need to consider these two. That's why it is 12 minus 11.9 divided by the input voltage is changed from 220 to 200. That's why it is 220 to 200. This gives 0.5. Okay. This is what the regulation is. If you do into 100, you are going to get the percentage, but they have not asked in the percentage. That's why I am not going to do. It is just the regulation of power supply is 0.5. Then problem 5. Here an amplifier produces output of 2 volts for an input of 50 millivolts. Means there is an amplifier. We are applying 50 millivolts of input and output is 2 volts. If the input and output currents in this condition are respectively 4 milliamps and 200 milliamps, means respectively, here they have given respectively, means the input is 4 milliamps input current and output current is 200 milliamps. Here let me take the input current, I at input it is 4 milliamps and I at output is 200 milliamps. What we need to calculate? We need to calculate the voltage gain and also the current gain and power gain. So we know that voltage gain AV is equal to V output divided by V input, right? This is what the voltage gain is. They have given the V out as 2 volts and V in as 50 milli. That's why it is 2 divided by 50 into 10 raised to minus 3. Remember, milli in the sense it is 10 raised to minus 3, micro in the sense it is 10 raised to minus 6. So voltage gain it is, that's why I am taking V out divided by V in. It gives 40. 40 is the voltage gain. Similarly, current gain. What is current gain? AI I can write. So I out, output current divided by input current, I in. Output current is 200 milliamps to 4 milliamps. So if you take this, it is 50. Now we need to calculate the power gain. What is power gain? What is the expression for power here? P is equal to V into I. So power gain AP can be written as, we can write here, I out into I out divided by I in into V out divided by V in. We can also write like this, and if you substitute these values, 200 milliamps divided by 4 milliamps is a current in into 2 volts divided by 50 millivolts. If you calculate this, you are going to get 0.4 divided by 200 microwatts, power in watts. So it is 2000. Okay. Otherwise, you can calculate this power gain. Let me write it as AP as AI into AV also. This is P is equal to I into V or V into I. So we have calculated the power as well as the voltage gain here, so that we can calculate the total as 2000. This is how we can solve the problems on this amplifier. Then the next problem is on the frequency response. Okay, determine the mid-band voltage gain and upper and lower cutoff frequencies for the amplifier whose frequency response is shown in the figure. This is the frequency response. You guys know that this is the gain in y-axis. In x-axis we are going to take frequency. They have given some curve and also they are given some values for gain as well as frequency. We need to find out the voltage gain, mid-band voltage gain, and then upper and lower cutoff frequencies. First let us calculate gain, mid-band gain. Mid-band gain in the sense it is AV. This is the gain we will be having. The maximum gain they have given, it is 35. You can observe here, right? 35. Mid-band gain in the sense we need to take 3 dB lower if it is represented in dB, or we need to take 0.707 times the maximum gain. So it is AV cutoff, we can call it is 0.707 times AV maximum. So what is the value we are going to get? It is 24.7. Here only they have given in the problem, it is 24.7, the mid-band voltage gain. And we need to calculate the upper as well as lower cutoff frequencies. For this, if you take 3 dB lower or 0.707 times this maximum, we are going to get these 2 points. Okay, if we project this to x-axis, we are going to get these 2 points, and in the graph only they have given F1 and F2. This is lower, or we call it as lower cutoff frequency, and this is called as upper cutoff frequency. That is F1 is equal to 57 Hertz and F2 is equal to 590 kilohertz, and this is lower cutoff frequency, it is upper cutoff frequency. Okay, it is easy to solve. Then we'll go to the next problem, an amplifier with negative feedback. This problem is on negative feedback applied to as an open loop voltage gain of 50. Okay, open loop voltage gain means there is no feedback connected, and 1/10 of the input is feedback to the input, where beta is equal to 0.1. They have directly given beta. Determine the overall voltage gain. Overall voltage gain means including the feedback with negative feedback is applied. Here they are connected an amplifier, okay, with negative feedback, that is beta. Okay, I hope you guys know what is negative feedback, right? This is an input and here we are going to take the output. We need to calculate the overall gain. What is the overall gain of the amplifier? Here they have given the open loop gain AV is equal to 50, and also they have given the feedback factor, it is 0.1. We need to calculate overall gain. What is overall gain? It is, let me call it as G. It is AV divided by 1 plus AV times beta. This is the overall gain if we connect the negative feedback. So substitute 50 divided by 1 plus 50 into 0.1. Okay, it gives I guess it is 8.33. This is the overall gain of the amplifier. By connecting the negative feedback, what happens? The gain reduces. Here you can observe AV is 50. After connecting the feedback with the feedback factor is 0.1, we have reduced that gain to 8.33. And then the next problem, that is with respect to the problem 7 is concerned. This problem is continuation with the problem 7. Here what they have given, the amplifier's open loop gain increased by 20%. Suppose if we increase the amplifier gain AV, okay, open loop voltage gain, that is AV, to 20%. 20% we are going to increase. What happens? Determine the percentage change in the overall gain. If 20% increment in the amplifier gain, what is the overall gain change? We need to get that in the percentage increase. So let us calculate new AV. What is new AV? It is changed by 20%. 20% in the sense it is 20 divided by 100. For 100 it is 20 into AV. Okay. Previously we will be having some value. I am going to add that. Since it is increase, I am increasing. Okay. So it is 0.2 times AV plus AV. Previously AV is 50. Okay. Then we are going to get the value as 60. The new AV I am getting here after 20% increment is 60. Okay. Now let us calculate the overall gain. The overall gain, that is G is equal to AV divided by 1 plus AV into beta. If we substitute 60 divided by 1 plus 0.1 into 60, it is 8.57. This is the new overall gain, right? After the 20% increment, we are going to get the overall gain as 8.57. Now we need to calculate the percentage increase in overall gain. Let us calculate percentage increase in overall gain. Okay. The percentage change in overall gain in the sense, previously we got 8.33 as gain. Here you can observe without 20% increment we got 8.33. So let us write old gain, that is G. Old gain is 8.33. The new value of gain is 8.57. Okay. Now we need to calculate the overall gain. Means if we calculate the percentage change in overall gain, we need to take the difference between the new gain minus old gain we need to take. So this with respect to the old gain, we need to calculate the percentage increase, not only the change. That's why old overall gain into 100. If you do, it gives the percentage. Okay, let us take new gain is 8.57 minus old gain is 8.33 divided by 8.33 into 100. It gives the percentage change, that is 2.88. So 2.88% of gain is changed when we have increased the open loop gain by 20%. This is how we can solve this problem. Okay, let us stop here. I will upload one more video on this problems with respect to the next topics are concerned. Thank you.